Welcome back. Okay, today we're unpacking the incredibly complex, really high-stakes world of EV fleet electrification. And we're diving into the absolute latest 2026 industry intelligence to decode what is, honestly, a massive global puzzle. Now, if you're tracking the transition to zero-emission transport, you already know it's accelerating fast, but it's also hitting some major roadblocks along the way. So this explainer is going to break down exactly what those roadblocks are, and more importantly, the really fascinating ways the industry is engineering around them.
Right out of the gate, I want to pose a question directly to you. Think about it for a second. What's the single most common reason that fleet electrification programs fail to scale? Is it the costs of the trucks? Maybe battery range? Actually, it's neither. The biggest point of failure isn't the vehicles themselves at all, it's the charging infrastructure. If you get the charging wrong, it'll literally sink a fleet before a single tire even hits the pavement.
Okay, let's dive into this. Here's our roadmap for the explainer. 1. An infrastructure engineering problem. 2. The supply chain bottleneck. 3. The fleet energy depot. 4. Startups bridging the gap. And 5. The autonomous charging imperative. Let's just get right to it. Section 1. An infrastructure engineering problem. To really get this, we have to completely shift our mindset from a simple consumer act to a highly complex industrial challenge. For a typical consumer, EV charging is basically just finding a public station and plugging in, right? It's a convenience problem. But fleet EV charging, that is a hardcore infrastructure engineering problem. You absolutely cannot just naively plug in 50 electric delivery vans at the exact same time at the end of a shift. The fundamental design principle for fleets is this: you must charge during dwell time, not during operation. Every vehicle spends time parked, whether that's overnight, hanging out at loading docks, or between shifts. That dwell time dictates everything. To understand how this plays out in the real world, we categorize charging archetypes, and notice how vastly different the power levels are depending on the vehicle's turn cycle. See, you have a school bus that sits parked for 8 hours overnight. Well, you really only need depot AC Level 2 power, which is about 7 to 19 kilowatts. It's the lowest capital expenditure because you have plenty of dwell time. But if you're running a regional transit bus that only stops for an hour, you need depot DC fast charging pushing up to 350 kilowatts. And for those heavy Class A trucks, you're looking at megawatt charging systems. The golden rule here is pretty simple. The power level must always follow the specific dwell time of the vehicle.
Section 2. The supply chain bottleneck. Here is where the beautiful math on paper crashes into the harsh reality of deploying hardware on the ground.
You might know exactly what kind of charger you need, but getting the actual power to it is a completely different story. And the hardware holding up the entire industry, it's not some super advanced microchip. It's actually the humble distribution transformer. See, there's a massive shortage of a specialized material called green-oriented electrical steel, or GOES. There's only one domestic manufacturer in the US, and right now demand from data centers, grid hardening, and these EV fleets is just going through the roof.
Because of that steel shortage, combined with lingering pandemic constraints, the data we're seeing is staggering. The Alliance for Transportation Electrification reports that average lead times for distribution transformers spiked a massive 429% between 2020 and 2022. It's almost unbelievable, but for some utilities, getting just one of these transformers can take up to 3 full years. 3 years just to get basic grid hardware on site. This creates a totally brutal timeline for operators. When you look at interconnection delays, you're looking at 12 to 24 months just for a standard depot. If you need over 1 megawatt of power, which, by the way, is super easy to hit with fast chargers, you could be waiting 24 to 36 months for a medium voltage interconnection. Even basic things like switchboards and panels are delayed. 1 in 5 utility projects have actually been deferred or canceled because of this. The absolutely crucial takeaway for any fleet operator is that you have to engage the utility 12 to 36 months before your first vehicle even arrives. If you don't, the program's going to fail.
Section 3. The fleet energy depot. So the obvious question is, how do fleet operators circumvent these massive grid limits and avoid astronomical utility bills while they wait?
The answer lies in completely redesigning the depot itself. We're moving away from just installing chargers to building a fully integrated microgrid, which the industry calls a fleet energy depot. And you build this sequentially. Step 1 is the EV-SE array, your actual chargers, but deployed in stages. Step 2 is adding a BESS, an on-site battery energy storage system. This battery slowly sips power at night and dumps it into the trucks during the day, which shaves off peak grid demand. Step 3 is solar PV to offset the site's auxiliary loads. Finally, step 4 ties the whole shebang together, a charge management system. This acts as the brain, orchestrating every single charging session so you literally never overdraw from the grid.
Now, what's really wild about this architecture is the sheer financial impact. If you naively plug in 50 fast chargers all at once, the utility is going to hit you with what's called a demand charge. It's a massive fee based strictly on your highest 15-minute power draw. It is the single biggest hidden cost in fleet charging. But by using a fleet energy depot design to manage that 15-minute peak, the 10-year total cost of ownership difference for a 100-vehicle fleet can exceed $5 million. That is the difference between a profitable fleet and a bankrupt one.
Section 4. Startups bridging the gap. But let's be real. What if you simply can't wait 36 months for the utility to upgrade your transformer? This brings us to the innovative cavalry of 2026 stepping in to bypass traditional grid delays altogether. Let's rapid fire through some of the startups solving this. First up is BeeCharged. They looked at the grid delays and basically said, you know what, let's just bypass the grid entirely. They offer ultra-fast mobile and containerized chargers functioning as charging as a service. If you have trucks arriving tomorrow and zero utility connection, BeeCharged can drop a containerized, completely off-grid power solution right on your lot to keep you running. Then we have the specific nightmare of urban bottlenecks, which is being addressed by a startup called It's Electric. In cities, digging up sidewalks for new transformers is just a non-starter. Their brilliant solution is deploying curbside chargers that tap directly into a building's existing unused electrical capacity. It requires minimal civil works, provides essential charging to the community, and it even generates passive income for the property owners. It's a real win-win. And this innovation is truly global. Take BeeCharged network out of India, for example. They are disrupting the entire landscape by decentralizing it. Instead of waiting around for massive top-down grid projects, they're deploying community-owned, AI-powered smart chargers. It just goes to show that intelligent software and decentralized hardware can absolutely leapfrog legacy infrastructure limits. Section 5, the autonomous charging imperative. Let's move on and see how this all builds into the ultimate endpoint of fleet evolution. We've solved the power, we've solved the grid, but what about the human element? Welcome to the era of robotaxis and autonomous fleets. Think about it. An autonomous vehicle cannot plug itself in. Today, we're seeing the actual hardware being deployed to allow machines to charge machines. You have conductive docks, where a robotic arm from a company like Roxas uses AI vision to physically plug a standard cable into a truck. Then you have inductive, or wireless charging, from companies like InductEV, where a robotaxi just parks over a pad and power crosses the air gap. And finally, mobile charging robots, which is literally a battery on wheels that drives itself over to a parked vehicle in a geofenced depot. Which brings us to this incredibly powerful insight from our sources. Autonomous fleets are not truly autonomous if charging requires human intervention. This is the ultimate paradox of the next decade. Look, if you run a 24/7 driverless truck operation, but you still have to pay a team of humans across 3 shifts to walk around the depot plugging cables into ports, you haven't actually eliminated the labor cost. You've simply moved the human from the cab of the truck to the parking lot. Autonomous charging isn't a luxury. It is a strict structural requirement for the economics of driverless fleets to actually work. And that leaves us with this final provocative thought to wrap up our explainer. We are standing in a massive crossroads right now. Will our traditional centralized utility grid catch up to these massive fleet demands, overcome the transformer shortages, and power the transition? Or will these decentralized, AI-driven off-grid startups permanently redefine how we power the future of transportation? The tension between legacy infrastructure and startup innovation is exactly where the real future of energy is being written. I hope this sparks some curiosity for you today. Keep learning, stay focused, and we'll see you in the next explainer.